Welcome back. We're in section 2.5, and this section is titled Matrix Transformations, Rotations, and Dilations. And the phone booth, which I don't even know if these exist anymore, but back in the 70s, Superman used these guys to, he would go in as Clark Kent and he would come out of the phone booth as Superman. And I want us to think about, this is this boxy thing that one thing goes in, and then Clark Kent comes out a totally different thing. We are going to see more and more matrices as transformations, as these sort of boxy things that are going to take a vector and transform it into a new vector. So just like this phone booth was a place of transformation, matrices we're going to see in this section, in the next section, and hopefully for the rest of the course as these sort of vehicles of transformation. So say that you're at work one day and your boss comes in and he says, I have these 1,000 vectors and I want you to rotate them pi-8 degrees. And we shouldn't say pi-8 degrees, we should say pi-8 radians. Because pi-8s were in radians mode. So your boss has asked you to do this job. You have 1,000 vectors and you've got to take each vector and rotate it. So if you have this vector here, you're just going to rotate it slightly, pi-8 radians, and get a new vector. And he's going to want the coordinates for the new vector. So maybe this is the first vector that you pull out of the box and its coordinates are 6, 2.85, and you think, okay, I've got to rotate it pi-8 radians and get the coordinates for the new vector. It'll be sitting right here. And there's all sorts of trigonometry you're going to use, and it's kind of an involved process to rotate it like that, but you do it. And then you do the second one and the third one, and each one is taking a long time. So you think, I wonder if there's a more efficient way to do this. I wonder if there's a tool that I can create that would just take any vector and rotate it pi-8 radians. So if I just had a generic vector and I wanted to rotate it, it'd be nice if I had a tool that would do that for any vector. Then I wouldn't have to go through the trigonometry each time. Okay, so that's the plan. We are going to make a tool that will rotate any vector we want pi-8 radians. So if I rotate this vector, I'll get a new vector that looks something like this. And we're going to call that x prime, y prime. So that vector is sitting at these coordinates. And actually I'm going to stretch it out a little because the length itself stays the right length. It just got rotated. Okay, so I think this picture is a little bit more accurate. And we'll say that this angle here is alpha. And we know that this angle here is pi-8. That's how much we rotated it. And so my first question is, do we know this length right here? We should. It's just the x-coordinate. So that length right there is x. From there to there is x. And then from here to here, this length here is going to be y, because that's the y-coordinate. We're going to call the length of the vector r. So that's just from the origin to the very tip, the length of that vector. And so then I can ask, well, what's the length of this vector? If it's just a rotation, the length stayed the same. So the length of that vector would also be r, the exact same number. So if this had length 5, this would still have length 5. Or if this had length 20, this would still have length 20. And then in a way that we saw similar to the original gray triangle, this length right here would have to be what? It would definitely have to be that new x prime, the new x coordinate. And this length here, this distance, would have to be y prime, the new y coordinate after our rotation. Okay, at this point we're going to start just pumping out the trigonometry. Okay, at this point I'm going to need a little bit more room, so I'm going to have to get rid of some of this stuff because we're going to talk about a couple important trig things. And the first one is Sohcahtoa. This is the way I learned trig identities. And so let's use that. Hopefully you learned it that way too. This just represents sine. When you have a right triangle, sine of an angle is the opposite over hypotenuse. And the cosine of an angle is the adjacent side length over the hypotenuse length. And then tangent of an angle is opposite side length over adjacent side length. So if I was looking just at the gray triangle, I could say that the sine of alpha is the opposite over hypotenuse. So y over r. So then just multiplying both sides by r, I get that y all by itself equals r times sine alpha. Let's do the same thing for cosine of alpha. I know that the cosine of alpha, this angle right here, if I'm looking at this gray triangle, the cosine of alpha will be the adjacent side, which is x, over the hypotenuse. So x over r. And so if I know cosine of alpha is x over r, then I can just do the same thing, multiply both sides by r, and I get x equals r cosine alpha. So I want to hold on to these guys. Now I'm going to concentrate for a minute on the red and pink triangle here and do pretty much the same thing. So for this red-pink triangle here, I want to use my trig functions, but now I have to think about what this angle is right here. It's alpha plus pi eighths. So if I'm thinking of the sine of alpha plus pi eighths, that will be opposite over hypotenuse. So that's this length, which is y prime over r. So sine of the sum of these is y prime over r. So we've got this relationship just coming from how trig functions work. And then I'm going to do the same thing, multiply both sides by r and find out just what y prime is. So all I did was multiply this r on both sides and I get this equation here. And I'm going to do the same thing for the cosine of this angle. The cosine of this angle, looking at this larger triangle, let's see, cosine is adjacent over hypotenuse. So the cosine of this angle here will be x prime over r. And then just like we did here, here, and here, I'm going to multiply both sides by r and find out just what x prime is. And just like it should look to, you know, we've already done this 3 times, and so we would expect it to turn out like this. Why did I go through all this? Our whole goal is, you know, your boss asks you to do this 1,000 times, so it would be nice if you had a vector and all you knew were the coordinates of the vector, and you know the angle that he wants you to rotate it, that you could input those 2 things and spit out what the new vector's coordinates would be. So these would be sort of like some inputs, and then we have some sort of transformation, and then we get an output. And we want some kind of formula, but not like in the olden days when we were in algebra and we would have a formula. We're in linear algebra, so we're in, you know, maybe multiple dimensions. So what we want and what we're going to end up doing is finding a matrix that will represent this transformation and give us this output. So we're trying to relate all of these things, these 3 things, and we're doing a pretty good job. We have x's and y's, y prime, x prime, and we've got a pi eighths in here. We need one more super tool from trigonometry, and then we'll be all set. So long ago in trigonometry, you learned that if you want to take the sine of a sum of 2 angles, that you could actually split that up using this formula. And I learned it too, but I can never remember it, so I always have to look this guy up. But so this is the sine of the sum of 2 angles, but interestingly, you can kind of split up those 2 angles, and that'll be valuable because we're going to use it with some of this. We're going to get the cosine version also. So I have y prime equals r times this, but instead of this, I'm now going to use this formula up here. And so we can say that y prime equals r times the sine of the first angle times the cosine of the second angle. We better put some brackets around there, plus the sine of the second angle times the cosine of the first angle. And then I went ahead and just multiplied this r all the way through. Okay, so at this point I can start substituting a few things. I have y prime equals r sine alpha. But r sine of alpha is the same thing as y. So I can put in, that's just y times cosine of pi eighths. And then over here I have r sine of pi eighths times cosine alpha. Well, r times cosine alpha, if I stuck those two together, that's just x. So this is x times sine of pi eighths. This is a great place to arrive at because I now have a relationship between y prime, y, x, and the angle that we're rotating through. And that's pretty much all there is to this equation. So this is really a big deal to find this relationship. I'm going to do something similar with these guys. I'm going to use this formula this time. So now I'm going to rewrite this equation, but right here I'm going to substitute this cosine of the sum of two angles for all of this right over here. So that'll give me x prime equals r times cosine of the first angle times cosine of the second angle minus sine of the first angle times sine of the second angle. And then I'll go ahead and distribute that r through. So my r is distributed through. I'm done with the brackets. And I can see that I've got some familiar things here. R cosine alpha, that's just going to be x. And then I've got r sine alpha, and that's just going to be y. So I can go ahead and substitute those in. So you can hear my husband and son in the background watching some NBA game. Okay, so we've arrived at this, and I know you think that's no big deal, this doesn't look that awesome, but it really is awesome in the same way that this is awesome, because we now have x prime, a relationship between x prime, x, y, and just this angle here that we're rotating through. So we could, knowing, you know, these three things, we could totally find what x prime is, and that's exactly what we wanted. So I'm now going to try to come up with a matrix that will take my x and y coordinates before the rotation and yield the x and y coordinates after the rotation. And I'm going to start by using this. I know that x prime comes from this times cosine pi eighths minus this times sine pi eighths. So what if I do something like put cosine pi eighths right here, and then maybe a negative sine pi eighths right here? Let's see what that would give me in the multiplication. I'd have x times cosine pi eighths plus y times negative sine pi eighths equals x prime. That sounds perfect. Okay, for this guy, how about if I put, let's see, I would want a sine pi eighths, and then how about a cosine pi eighths right here, and let's see if that gives me what I want. So sine pi eighths times x, good, plus cosine pi eighths times y, good, equals y prime. I got it. So Clark Kent here goes into the telephone booth and comes out as Superman. This matrix is a transformation. It will take any vector and it'll rotate it through pi eighths and give you the coordinates of the new vector. So this is the tool that you needed when your boss came with 1,000 vectors and wanted you to rotate them pi eighths radians. You could say, give me 10,000. I've got this awesome tool that'll just spit out the numbers. So we now have a matrix that will take any vector, and we should say that that vector needs to be in R2, and rotate it through an angle theta. Last time we were using alpha, but you can use any Greek letter that's commonly used for angles. Rotate it through an angle theta about the origin. Okay, the way we're going to write this is this capital T stands for transformation, and here's our input. We're inputting vector xy, and then we know, we've already figured this out, we know that this has to equal cosine of the angle that we want to rotate through, and this is negative sine of the angle we want to rotate through, and then sine of theta and cosine of theta. If we take that matrix and multiply it by xy, we will get the coordinates of the new vector. So this is the a matrix that will take any vector in R2 and rotate it through an angle theta. And this is called a matrix transformation. This is one example of a matrix transformation. We'll see a couple others in this section. Let's run through one example. We're going to rotate the vector 3, 7 through the angle pi halves. And when we take that vector 3, 7 and rotate it through pi halves, we should expect to see a vector, our new vector, looking something like this. So we will use our matrix transformation to transform 3, 7 through pi halves. We're going to take this matrix and multiply it by our original coordinates. So without too much thought, I remember that cosine of pi halves is 0, and I remember that sine of pi halves is 1, so this is a -1. And I remember, well, sine of pi halves is 1, just like we just said, and this should be 0 here. And we're going to multiply that matrix by the vector 3, 7, and it looks like we get -7, 3. Does that sound reasonable? Yeah, -7, 3 is probably about right. So any starting vector, any angle, this is the guy for your job. He will rotate your old vector into a new vector through this angle. So in the olden days, when we were just dealing with real numbers in algebra, algebra 2 or college algebra, we called these things functions. Now, as we're dealing with multiple dimensions and even going back and forth between dimensions, we call these matrix transformations. But they're doing a lot of the same job. You have an input, you put it through this transformation, and you get an output. You can even see in the notation, this is reminiscent of the olden days we used to have f of x, right? When we were just dealing with real numbers to real numbers. Now we're going to take a transformation and we have an input that's going to be some sort of vector, and we're going to get out of that transformation. This is the rule for this particular transformation, sort of like the equation for it, and we get out of it some output. And you can even go from, here we are in R2 and we got something in R2, but you can go from R2 to R3 or R2 to R7 or R7 to R2. So back and forth between different dimensions. So here this transformation is going to take something from one vector space like Rn and transform it into another vector space Rm. It could be the same vector space, but it doesn't have to be. So the transformation T is a rule that assigns each vector in Rn to a vector in Rm. So this particular transformation is a transformation from R2 back into R2, and it's called the rotation matrix. This vector was living in R2, and it got transformed into another vector that was also in R2. Okay, we're going to change gears a little bit, and now we're going to find a matrix that will... This time we're going to find a matrix that will dilate the vector 2, 5 by a factor of 3. So think about this vector right here, the vector 2, 5, and we're going to try to dilate it by a factor of 3. So we're going to make it 3 times as long. And we want to know where that ends up. Essentially, we want to find the matrix. Actually, that's the example. That's what they've asked us to do. So the transformation that they're asking for is a transformation from the vector space R2 right back into R2, because these vectors both live in R2. And whatever this transformation is, we want it to take x, y, and we want x to grow by a factor of 3, so 2, 4, 6, and we want y to grow by a factor of 3. So we think about what possibilities there could be. We want x to grow by a factor of 3, but no y. That would give us 3x. And we want y to grow by a factor of 3, but nothing to do with x this time. And that would give us the 3y that we need. Perfect. Okay, so this is actually the transformation. I was just kind of scratching that out. But the real answer, the thing that they're asking for, is this guy right here, and essentially this matrix is the transformation. So this is the answer to the problem that they've given us. Okay, this time they ask us to find a matrix that will contract 2, 5 by a factor of 1/2. So this vector 2, 5 is going to be just half of its size. And it's not too hard to figure out what we want that matrix to be, about 1/2, 0, 0, 1/2. this would give us exactly what we want. If we have xy, then it will give us out 1/2 xy, or 1/2 x, 1/2 y, which is what we need. So this is the right matrix for that transformation. So this is a class of transformations called dilations and contractions. For our next example, we're asked to find a matrix that will something the vector AB, so just some generic vector AB, across the y-axis. Well, if we're going across the y-axis, then chances are we're doing some sort of reflection, so we're going to reflect the vector AB across the y-axis. This is going to be a transformation that takes some vector in R2 as our input and spits out another vector in R2. It's just a reflected vector, but it's still in the same vector space. Let's see, so we want some matrix that when we multiply it by AB, what do we get out? Let's see, AB is this vector, and we're going to reflect it across the y-axis. So then we get something that looks like this, and the coordinates of that should be, it still has height B, but now this changed not to A, but negative A. So we want it to spit out negative A, B. And so we think about what needs to go in these spots to make that happen. This would probably be a negative 1, 0. That'll give us negative A. And how about 0, 1? I think that's it. So these types of transformations are a lot more simple than those rotations that we started this section with. And so this would be a way to write the transformation formally. The transformation whose input is the vector xy is equal to this matrix times xy. And so far the matrix transformations that we've seen are rotation, dilation, and contractions. And now this last one we saw a reflection. And we don't always have to reflect about the y-axis. We could reflect about a lot of things. We can reflect about the x-axis or the line y equals x, but this last type is a reflection. So one question we can ask is, what if we want a combination of these transformations? What if I want to do a dilation followed by a rotation? Is there an efficient way to do that? So this time your boss comes and he has 1,000 vectors, and he asks you to please dilate them by a factor of 2. And then when you finish that, rotate them by pi-thirds radians about the origin. And so you start getting all ready. This matrix right here will perform the dilation. And then I have this matrix that will perform the rotation for me. And we can clean this guy up a little bit. I know that cosine of pi-thirds is 1/2 or 0.5. And negative sine of pi-thirds is going to be negative square root of 3 over 2. Sine of pi-thirds will be square root of 3 over 2. And cosine of pi-thirds is that 0.5 again. So I take my first vector from the pile of vectors he dropped off. You know, I have my other 999 right here. And I'm going to first take it through the dilation. And I take it through the dilation and I get 10, 14. Now I'm going to take this vector and run it through the rotation. So I have my rotation matrix here, and I'm going to multiply it by 10 over 14. And let's see, that should give me, this is 5, and then minus 7 square root of 3. So 5 minus 7 square root of 3. And I could get a decimal number for that if I wanted. And then I've got, let's see, this times this will be 5 square root of 3 plus 7. Okay, and that's it. I did the first vector. Now I just have to run through all the other vectors. So what I essentially did is took my vector, u1, and multiplied it first by that dilation matrix. And then once that was done, the vector that resulted from that, I multiplied my rotation matrix by that. But now after going through that process that first time, I'm starting to see that actually I probably could cut my workload in half, because right off the bat, why don't I multiply these two matrices together, and then I'll get another matrix, just one matrix, that I have to run through all the vectors. And that would save me 1,000 steps. So combining these two matrices will essentially combine the dilation and rotation into just one step. So I decided I'm going to multiply these two matrices together to combine those two steps into just one step. And so here I'm going to do it. And of course I have to do it in this order because it's the A1 vector that hits the A1 matrix that hits the vector first, and then the A2 matrix. And when I do this multiplication, I will get 2 times a half is 1, and this row by this column is negative square root of 3. And then this row with this column is square root of 3. And lastly, this guy with this guy is 1. So this one matrix here will perform both operations. So this one matrix will perform both the dilation and rotation in the right order. So let's give a formal definition of these composite transformations. We saw this example here. But we could really have more than 2 transformations. We could have up to n transformations all in a row. So let T1 through Tn be a sequence of transformations defined by the matrices A1 through An. Then the composite transformation is just the product of the matrices. So T is Tn composed. Remember, this guy right here is an operation that means composed with. So Tn is composed with Tn minus 1 composed all the way to Tn. And that will equal, those aren't matrices yet, the matrices are the A parts. It will be A, let's see, should this be 1 or n right here? Definitely needs to be n, and this is n minus 1. And now these are all multiplied, A2 times A1. Because you want the A1 to be on the right side, it's got to hit the vector first. It's got to operate on the vector first, and as soon as that's done, the A2 can. But the point of all of this is you can take those n matrix transformations and smoosh them all together, multiply them all together, and you will create just one matrix. And at that point, all of this work can be done just by one matrix. That's a really awesome thing about how matrix multiplication works. At this point, before we go on, we want to make note of one thing that we mentioned earlier. And it's this idea that transformations can move vectors between dimensions. So you might have a transformation that takes a vector from R2 and moves it into R5, for example. Okay, so let's take a look at an example like this. So we'll let T be the transformation defined by this matrix here. And so T is going to be a transformation from which vector space into which vector space. So you have to think about how this is going to go. You're going to take this matrix here and you're going to multiply it by some vector. What size does that vector have to be if we're multiplying by this guy right here? Well, these rows have to match up with these columns. So I'm pretty sure that we have to start at least in R2. And then where are we going to end up? Well, when we do this multiplication, we're starting in R2, and we'll take this row with this, and we'll get an element, and then we'll take this row with this and get an element, and this row with this, we'll get an element. So it looks like we're ending in R3. So this is a transformation that's going to take vectors in R2 and transform them into vectors in R3. And so the job they want us to do is find the image of this vector and this vector. So to find the image of those vectors, we just take the transformation matrix and multiply it by the vector. So it looks like over here we'll be getting -1 plus 2 is 1, and 1 plus 3 is 4, and one more, -1 plus 2 is another 1. So this is the image of, this vector went through this transformation and came out like this. Okay, the next one should expect the same size, and we get, let's see, 2 plus 6 is 8, and -2 plus 9 is 7, And 2 plus 6 again is 8. Last topic for this section, we get to talk about orthogonal transformations. And these are just a special type of transformation. It does happen sometimes that a matrix, the inverse of the matrix, is actually equal to the transpose of that matrix. And when this happens, it brings out some special properties. These are called orthogonal matrices. So when you're a matrix that your inverse equals your transpose, you are an orthogonal matrix. And when we're using these matrices as transformation, then this is called an orthogonal transformation. So you might ask the question, why do we even care about this? What's so cool about this relationship? One reason these orthogonal transformations are so important is because they preserve three things. And when we say that a transformation preserves something, it means that, before a characteristic from before the transformation is still there after the transformation. And the three things that these orthogonal transformations preserve are norms, so lengths of vectors get preserved, and angles. So maybe the angles between two vectors, you take those two vectors through the transformation and they will still have the same angle between them, and also distances. So these three things, this geometry is preserved even through the transformation. That's not typical of your random transformation. These things don't always get preserved, but with orthogonal transformations, a vector goes through the transformation and it will still have the same length. It will still, between that and another vector, it'll still have the same angle, and distances between vectors will be preserved. Another word for these types of transformations are that they're rigid motions. So I want to ask you a question at this point. Of the three types of transformations that we've looked at so far, we've looked at rotations, contractions, and dilations, and the third one was reflections. So some of these are orthogonal transformations and some aren't. And can you guess which ones are orthogonal? So I'll tell you that 2 of the 3 are orthogonal transformations and 1 of the 3 is not an orthogonal transformation. So try to think about which one of those transformations we've already talked about doesn't preserve these 3 things. And we'll talk about it in a minute. But first, let's look at an example. So I'm looking at this matrix right here as a transformation. A is all of these guys. And looking at it, I'm getting a little suspicious. All these square roots of 2 remind me of trig and some sine and cosine. So maybe it has something to do with that. Maybe it doesn't. But all I know is this is I suspect this is an orthogonal matrix, and we're going to verify that it is. And I also start with these 2 vectors. This is vector u, and here I have vector v. Right off the bat, let's find the norm for each of these vectors, so the length of these vectors. And this is going back to section 1.6, where we talked about a lot of these ideas, but we know we can find the norm of this vector. And the norm of u is just this formula. We'll take the square root of each of the elements squared and added together. So the norm of u is 2, and the norm of v will be the square root of 3 squared plus 4 squared, and that's the square root of 25. So the norm of v is 5, the norm of u is 2. Let's take both of these vectors through this transformation and see if the resulting vectors have the same norms. And we'll start with u. We'll take u through the transformation. So u is our input into this transformation. And so we'll take the matrix A and multiply it by the vector u. And when I do this multiplication, I will get 2 over the square root of 2 and negative 2 over the square root of 2. This is the transformed vector. So let's find the norm. Let's find the length of this transformed vector. So the norm should be the square root of each of the elements squared and then added together. And this guy, when you square it, it just becomes 4 over 2, which is 2. Same story over here, 4 over 2, which is 2. We get the square root of 2 plus 2, which is the square root of 4, which should be 2. So the norm of the transformed vector AU is 2. That's awesome because it just preserved this norm. This vector went through the transformation, but it was still the same length when it came out. That definitely doesn't happen with all transformations. It is preserved because this matrix is an orthogonal matrix. Okay, we're going to do the same thing with the vector v. It did have a norm of 5, so we're going to take v through the transformation, and we get this vector out. So this is AV here. Hopefully it also has a norm of 5. And so I do this work to find the norm of AV. I put in each element, square it, and add them together, and then take the square root. We get 49 halves plus 1 half, and that's 50 halves, which is 25. The square root of that is 5. So awesome! This norm was also preserved through this transformation. So all of this work here just was showing me that for these two particular vectors, the norms were preserved through the transformation. You should also know that the distances were preserved. So I went ahead and did all this work to find the distance between u and v. This one wasn't too bad. The distance is 4.12 units. And then I went ahead and found the distance between the transformed vectors. This one was bad, but it ends up also being 4.12. So the distances between those two vectors, the endpoints of those two vectors, stayed the same even through the transformation. And last but not least, we will see that the angles between the two vectors are preserved. This is actually, this transformation, you've probably guessed it, it's a rotation of pi/4 radians. That's where these numbers come from, the sines and cosines of pi/4. So the angles, I haven't even shown you the work, but the angle between u and v is 53.13 degrees. And you can find this, we have a formula from section 1.6 about finding the angle between two vectors. And then if we went through, here's AU and AV, if we wanted to find the angle between those transformed vectors, it's exactly what you guessed, it's the same angle. And that totally makes sense with a rotation because you're rotating everything, so those angles will be preserved. So while this all is not really a proof that this is an orthogonal transformation, it's a demonstration of, for two particular vectors, how the norms were preserved, how the distance was preserved, and how the angles were preserved. Why the heck does this relationship make it so that all of these things are preserved? And that is such an interesting question. Why is it that when the inverse of a matrix equals its transpose, that we get these rigid motions? So for our grand finale today, we do want to explore this idea. Why would this relationship, where the inverse equals the transpose, make it so all those things get preserved? Why would that force a rigid transformation? And the first part of the answer is it all depends on the dot product. Do you remember the dot product was instrumental in finding a norm and in finding distances and in finding angles? It shows up in each of those formulas. So if we can show that the dot product is preserved when this happens, then all of those other three things just fall out automatically. So imagine that we have a vector. It's started out as vector u, but then we pushed it through this transformation and out came another vector. And this is the new vector after the transformation. And we'll do the same thing to this vector v. It goes through the transformation, and so here essentially is a new vector, t of v. And we're going to take the dot product between this vector and this vector. And when we take the dot product between those two vectors, that equals, that equals AU, because A is the transformation matrix, dotted with AV. And remembering that when we multiply A and U, this is just a vector dotted with another vector. Okay, let's keep going. If we're going to take that dot product, then that's essentially like, well, think about what AU looks like. This is like a vector dotted with another vector. So be careful here between dot product and just regular multiplication. There's a big difference. We can say that this dot product, because of how dot products work, is the same as, well, let's take this as a row vector and multiply it, just matrix multiplication with that second vector. Then that is the same thing. This dot product is the same thing as this multiplication here. remembering what the definition of dot product is. So this guy right here is just AU transpose. So we have AU transpose multiplied by AV. It's not a dot product anymore, it's a matrix multiplication. So make sure you think through this step here. This is the big step right here, that we're taking the dot product and just redefining it as a matrix multiplication. After that point, everything really drops out because we know, because of rules of transpose, that this will just be U transpose A transpose times AV, and then A transpose is the same as, this is the big, we'll use this property right here, or this relationship right here, and we know that this is the same thing as U transpose A inverse A V, and then we get U transpose, just the identity matrix, V, and so that's just U transpose V, which equals the dot product of U and V. Sorry, I've been leaving off all these guys, but those are vectors, not scalars, all the way through. Okay, so what I've, just through this series of logical steps and these all these relationships, we've shown that when you take the dot product of the transformed vectors, it's the same as the dot product of the original vectors. When dot product is preserved, all of those other things, bam, automatically are preserved. Your norm, your angle, your distances, because all of those depend on the dot product. Okay, so this is sort of a proof that of why this would make those rigid transformations, because the dot product is preserved through the transformation. And it all depends on the fact that A transpose is the same as A inverse right here. Okay, so I know you've been thinking about what we were talking about, those three transformations that we talked about today, the rotation, the dilation contraction, and the reflection. Which ones were orthogonal transformations and which ones aren't? So first of all, think of contractions and dilations. Do they do the important things? Do they preserve all of these? Does a dilation preserve norms? Absolutely not. I mean, you're taking a vector and you're like expanding it, you're multiplying it by 3 or whatever. And so that norm is totally changed. So first of all, we definitely know that dilations, contractions are not orthogonal transformations. But both rotations and reflections are orthogonal transformations. We could prove it this way, but just thinking about a rotation, think about what a rotation transformation would do to any vector, and two vectors together, you would preserve everything. You'd preserve the norm, the length of the vector, you'd preserve the angle between vectors, and you would preserve distance between vectors. Same thing with a reflection. All of those things would be preserved. So these were three really fundamental matrix transformations that we wanted to talk about, and in the next section we'll see a few more. Okay, so we have some big ideas for today, but first I just wanted to make mention of, I wanted to write down all of the reasoning of why we went through this, because norm, angle, and distance are all dependent on the dot product. Once we know the dot product is preserved, the others are also. Okay, today's big ideas were, one important thing we talked about was the idea that matrices are like transformations, just like a function in the real number system back in algebra, just regular, algebra 2, whatever. Functions took an input and gave an output. This is essentially what matrices can do. You can think of matrices as these functions where you're taking vectors in, the matrix is going to transform it and spit out a new vector, and that vector doesn't have to live in the original vector space. You can take something from R2 and send it to R8. Okay, then three important transformation examples that we looked at were these three: rotation, dilation, contraction, and reflection. And then last but not least, we talked about the idea of an orthogonal transformation, that when your transformation has this relationship, it is a rigid transformation and will preserve all sorts of good stuff. Sorry, I thought I was done, but I remembered we have to tag on this guy. This is a really important topic we talked about, the idea of composite transformations, that maybe you have a list of, 17 transformations that you want to do, and they're all represented by matrices. And the power of matrix multiplication is that you can take these composite transformations and just multiply them all, smush them all into one matrix by multiplication, and that's so much more efficient. So composite transformations was another big idea we talked about.